was thinking about this introductory course to Keller geometry, and so basically my goal would be just to explain some basic Hodge theory to you. And so since I didn't know who will participate and so what is known and what is not, I decided just to make a very basic introductory lecture. So I'm sorry if you will know everything that I will explain today, and feel free to ask questions. Actually, I hope that you do know almost everything I will explain today. So I wanted just to recall, first of all, the definition of a complex manifold. So Keller geometry is basically about complex manifolds, and so we should really make sure that we understand what we are talking about. So let's start with this. So complex manifolds. All right, so I will just introduce some notation first of all. So if M, let's say we have some topological space, and we have some open cover of this topological space. So U alpha is an open subset in M. So this is an open cover. Then I will denote, as usual, the intersections of those open subsets like this. So this will be U alpha intersected with U beta, and triple intersections will be denoted like that, and so on. And now, so what is a complex manifold? So the definition goes like this. So one of the possible ways to define it is that a complex manifold of dimension M, so a complex manifold which will be denoted by capital M of a dimension small m, is a Hausdorff topological space with a countable base and an open covering with some continuous functions or continuous maps phi alpha from each of those open subsets into Cm such that so they satisfy the ordinary conditions. So first of all, phi alpha is a homeomorphism onto some open subset in Cm. And then if we denote by phi alpha beta the following composition, so phi alpha composed with phi beta inverse, and this will be so defined on some well, it is naturally defined on the image of the intersection u alpha beta like this. So these two things are just open subsets in CM, so this map should be holomorphic. So yeah, so that's the usual picture. If we have something like that, and we have this cover by charts, so and on the intersections there is a transition function phi alpha beta, right? So this is phi alpha, this is phi beta, and this should be a holomorphic map, and actually a holomorphic isomorphism between these two subsets in CM. Okay, so U alpha is U alpha with this phi alpha is called a chart, and this collection is called an atlas. And of course M is called the dimension. Well, that is already written. So in particular, any complex manifold is a real manifold of real dimension 2M. Right, so I recall that a map between two open subsets in CM, so let's say from U in CM into CM, so this map is just given by, well, coordinate-wise by some functions, and those functions should be holomorphic in each variable. So that is what is meant that the map is holomorphic. So we can write Wi equals Fi of Z1 and so on Zm, and the condition is that the partial of Fi over dZj bar equals 0. So that's the usual definition, and as an exercise you can exercise just to recall probably some notions from basic topology. You can think about this exercise at home, that just check that any manifold, a complex manifold, or even any real manifold is a normal and paracompact topological space. And also maybe you can check that it admits a partition of unity. So may I ask, so does everybody know what paracompact means? Okay, good, great. So everybody is familiar with these notions, so maybe the second part of the exercise is to check that for any open cover there is a partition of unity well, so how to say, subordinated to this cover, so that the support of every element of this partition of unity lies in one of those open subsets U alpha, so subordinate to the color. Okay, good. Then let's define now the structure sheaf. So let's denote for any topological space, well, let's say M again. M is a topological space. And then we will write C0M for the sheaf of continuous functions. So it means that for any open subset U, so this is just a collection of all continuous maps. Well, I will always assume that my functions are complex valued. For any open subset U in M. So now the structure sheaf of a complex manifold or of a differentiable manifold is a subsheaf in this C0M. So if questions? No? So I don't know, there are no people in Zoom now, well, but maybe someone will show up. So if M is now a complex manifold, let this structure sheaf OM, it will be denoted like this. So curly OM of U. So this will be the collection of all functions that satisfy the following condition, that they are holomorphic in every coordinate chart. So that for any alpha in the index set, so for any alpha, so the function which is the composition of f and phi alpha inverse, right? So this goes from phi alpha of u intersected with u alpha. So then phi alpha inverse takes me back to M, and then I apply f. So this goes to C. And so if I look at this function, so I should write that this is holomorphic. Is holomorphic. Okay, so this OM is a subsheaf of C algebras in the sheaf of continuous functions. And a different way to define the structure of the structure of a complex manifold on a topological space is just to give a sheaf of, to define a sheaf, a subsheaf of the sheaf of continuous functions that satisfies certain properties, namely that locally around every point, this topological space, so somehow every point has a neighborhood that is isomorphic to an open subset of Cm, and in such a way that under this homeomorphism, the subsheaf OM corresponds to the sheaf of subsheaf somehow to the sheaf of holomorphic functions in Cm. So we can write it so as a remark. So let me repeat this. So another way to define a complex manifold so M is a topological space. Again, Hausdorff, and with countable base, we always assume this to exclude some pathological examples. So Hausdorff topological space with countable base. And plus a subsheaf OM inside C0M such that every point in M has a neighborhood, so there is some open subset U containing this point and a homeomorphism phi from U to V, which is an open subset in Cm, right? So such that, well, so such that my sheaf is just the, well, it's the pullback of the sheaf of holomorphic functions on V, or I can write it in the following way: for any open U prime, for example, in U, so F is in OM of U prime, if and only if. Well, again, I look at this phi inverse composite with F. So this goes from some subset of V back to U, and then I apply this F. So this should be holomorphic. Okay. Right. So and of course it's easy to define the notion of a morphism of complex manifolds, either in terms of charts or in terms of this sheaf of holomorphic functions. So let's write down this definition just for the record. So if I have two complex manifolds, M n complex manifolds, and I have a, well, let's say with charts, with atlases U alpha, phi alpha, and for example V beta, psi beta, then a continuous map from M to M is a morphism of complex manifolds. Or a holomorphic map between complex manifolds if, well, again, if for any, so if it is holomorphic in any pair of charts. So I take two charts, so U alpha fits in M and V beta is in N. So then I should consider the following composition. So I take phi alpha composed, I guess the other way around maybe. So psi beta composed with f and composed with phi alpha inverse, right? So u alpha is here and v beta is here. And so this is defined on some, so it is naturally defined on some subset. So let's see, it is defined on phi alpha of u alpha intersected with the pre-image of v beta, right? And then it goes to psi beta of v beta. So anyway, that's a map from one open subset of Cm to some other open subset of Cn, and so such that so if this map is holomorphic. Okay, so as an exercise you can recall how to phrase that a continuous map is a morphism of complex manifolds in terms of the structure sheaves. So rephrase the definition of a morphism of complex manifolds. In terms of structure sheaves. Okay, so let's now prove something. So I was not going to prove too much today, but so there is one easy and nice proposition which we could easily prove and recall some basic notions from complex analysis on the way. So let's say now that M is a compact and connected complex manifold. Compact connected complex manifold. And let's say that I have some global section of the structure sheaf, and well, then I claim that this global section of the structure sheaf is a constant. So I'll write it like this. So then the global sections of the structure sheaf are just constants, so constant functions. Okay. Okay, so how shall we prove this? Does anybody know? So Liouville theorem, I would say it claims that a bounded holomorphic function on Cn is constant. So how should we apply this?
Well, maximum principle.
Yeah, that's right. So this I would like more.
Since M is compact, then modulus of f, where f is a holomorphic incontinuous function, achieves its maximum.
Yeah, correct.
But such a function is constant by maximum modulus principle.
Yeah, that is correct. So let's write this down. So if we have some function, then indeed, since M is compact, then so this function, the absolute value of f, so this is a function from M to R, So then M compact implies that this attains maximum. So let's say that this maximum at some point x0 in M. So then, so how do we argue after that? So to be precise, we should somehow look at the local chart around this point. So to be completely rigorous, so let's do it like this. So let's define f max to be the value of f at this point x0, and then let's look at this set. So let's call it M maximal. It's the set of points in M such that f of z equals this f maximum, right? So that's just the preimage of this complex number f maximum. So this set is closed and it is non-empty. And now since M is also connected, so it is enough to check that this M maximal is open. So this is closed and non-empty, right? So we should just check that it is also open. And this just follows indeed, as we know from the maximum principle from complex analysis. So if we look at some, so there is some chart U alpha containing x and x0, or well, let's better write it like this. So let's take some point in this M maximal and prove that M maximal contains some neighborhood of this point. So there is some U alpha, a chart containing x, and phi alpha maps U alpha into C M. So we assume that for example, phi alpha of x is 0 and the image is just an open ball with center at 0, right? And then we look at the function, which is well, let's denote it by g, which is f composed with phi alpha inverse, and this g has it has a maximum at 0, right, in this open ball, and G is holomorphic. So by maximum principle, G is constant, right? So then we see that also F is constant in this neighborhood U alpha, and so U alpha lies in M maximal, and this completes the proof. So by the way, how do we prove maximum principle? So what's the idea?
Well, we could deduce it from open mapping theorem.
Yeah, right. So I would also do it like that. So the idea is that if we have some, well, let's say we have some holomorphic map of one variable, right, defined on an open disk and attaining its maximum somewhere in the interior, but we know that a non-constant holomorphic function is an open map. So then, if the value of this function is bounded, so the image of the function lies somewhere in the set where the absolute value of z is smaller than or equal to f maximum, the absolute value of f maximum, right? So this means that the image lies in the closed disk of radius absolute value of f maximum, and somehow it intersects the boundary of this closed disk. But on the other hand, if the mapping, if f is not constant, then the image should contain some neighborhood of this point on the boundary, and this neighborhood will always go outside of the closed disk, right? So this part will lie outside, and this is a contradiction. Okay, so that's just a quick reminder about complex analysis. And now, so let's just talk about some examples. Well, basically we will study Keller manifolds, and so we would like to have some examples. Basically, let's discuss examples of so how can we construct complex manifolds? Some of them will be Keller and some of them will not, as we will learn later, hopefully. But okay, so let's just spend some time and list a few ways to construct complex, new examples of complex manifolds out of the old ones. So examples of complex manifolds. Well, the first example I want to recall is just the complex projective space. Well, it's easy to describe it using charts. So what is this? So this is the space of one-dimensional. Well, let's just so that the set, as a set, is just the set of one-dimensional subspaces in Cn+1, right? Or you can say that this is a quotient of Cn+1 minus 0 by the action of C star. So, well, every one-dimensional subspace is uniquely determined by some non-zero vector on it. Well, so we have the quotient map from Cn+1 minus 0 to Cpn. So let's denote it by pi. And as a topological space, it is just the, well, it is endowed with the quotient topology. So with the topology of the quotient, I'm not sure that I'm saying this correctly. So yeah, I think it's the quotient topology in English. That the open subset in Cpn is open if and only if its preimage here in Cn+1 minus 0 is open, right? And then we can cover this Cpn by the standard chart. So a point in Cpn is denoted like as usual. So z0, z1, zn. So these are homogeneous coordinates. And we have an open subset uj, for example, consisting of points such that zj is not 0. And then, well, we can consider a homeomorphism of this subset in CPN with Cn, right? Sending our point into the following. So we just divide everything by Zj. Like this. Okay, so this is a homeomorphism, as one can easily see. And one can check that the transition functions are actually holomorphic. They are even algebraic, as everybody knows, I guess. So is everybody familiar with this? Okay, good. So so then I will not do the computation, but you can, if you have not seen the computation, then you can do the exercise and check that these phi j's, they really define the structure of a complex manifold on this topological space CPN. So exercise, check that this gives a structure of the structure of a complex manifold on CPN. And then, of course, if we have this CPN, then what we really want is to consider submanifolds in it. So a submanifold is just a closed subset which is locally defined as the zero locus of several holomorphic functions. So not necessarily in CPN, but assume that we have just some complex manifold M, and so let's say we have some closed subset N, N is a subset of M, so this is closed, such that every point x in N has a neighborhood U. So this is an open subset of M containing this point x. And so let's just assume first that, let's say that this N is given as the zero locus of one holomorphic function. So let's say there is a holomorphic function on U whose differential is not 0 at this point x, and N intersected with U is just the zero locus of F. Right, like this. Well, then I claim that this N is also a complex manifold. So how can we see this?
By Halomorphic implicit function theorem.
Yeah, right. So I would also do it like this. Indeed. So if we assume, well, using these holomorphic charts, we can always shrink this U and assume that it lies in one chart, and then we can simply assume that U is an open subset in Cm, and then we have this function f whose differential is not zero at some point. So then by Halomorphic implicit function theorem, so I'll write it like this. So without loss of generality, we may assume that U is, so this U is a subset in Cm, and then by Halomorphic implicit function theorem, we can find local coordinates around x such that this f in those local coordinates z1 and so on, that m is simply z1, right? So then just like this. Well, then obviously n intersected with U is simply the set of points where the first coordinate vanishes. So this is a complex manifold, right? And then we can cover n by such open subsets and check that the transition functions are holomorphic. And so this defines the structure of the complex manifold. And more generally, of course, well, not every sub-manifold is given by one equation, but more generally, so let's call it 2 prime. So this example 2 prime. So n is again closed. So everything is as in 2 as above, but we have several functions, right? So the collection f1, fk, a collection of functions on U such that n intersected with U is just the common, the set of common zeros of all these functions, f1 of z and so on, fk of z. So they all vanish. And then what we should ask is that the Jacobi matrix, so instead of the differential, we consider this Jacobi matrix of this collection of functions. Well, so the Jacobi matrix of f1 and so on fk at this point x. So this is the point x around which I look at this neighborhood U. So the Jacobi matrix of this collection of functions at x, it should have rank k. Has rank k. And then we argue as before, but instead of this one, well, somehow then we can find the local coordinates, so that in those coordinates fi is just equal to zi, right? And then again we get just some linear subspace in this Cm defined by this condition, and this is also obviously a complex manifold. All right, so that's easy. Well, so that's one basic way to construct examples of complex manifolds. For example, now we can take polynomial functions well, polynomials, they are not functions on CPN, but somehow they define functions locally on these subsets, and we can consider well, the loci of common zeros of several polynomials, and if those polynomials satisfy this condition, that the Jacobi matrix at every point has rank k, then we get complex submanifolds of CPN. So they will not only be just complex manifolds, but will be actually algebraic varieties. And in particular, they will be the most important examples of Kähler manifolds. So there are more ways to get new examples of complex manifolds out of the existing ones. So let's, for example, discuss the following procedure. Well, of course, here we had closed subsets. Well, if we consider open subsets, they are also complex manifolds, obviously. But more generally, well, let's say again that we start from some complex manifold M, and then let's just take some map from some M tilde to M, which is a local homeomorphism. A local homeomorphism. Well, this means that every point in M tilde has a neighborhood U, open neighborhood U, such that the restriction of pi to this U is a homeomorphism from U onto its image in M. Then I claim that this M tilde is also a complex manifold, and we can construct these charts in an obvious way, of course, by covering M tilde by such U, by such neighborhoods. And if we need, we can shrink this U in such a way that the image of U in M is contained in some chart. And then we cover this M tilde by such neighborhoods, and we get an atlas, and we get a structure of a complex manifold. So I will not write down the details. I guess it's quite well clear how to do this. So M tilde is a complex manifold. So a particular example of a local homeomorphism is a covering. So every covering map is a local homeomorphism. An open embedding is a local homeomorphism as well. So, for example, every connected component of a complex manifold is a complex manifold, and so on. So that's all quite obvious. Well, let's then also discuss the following example. So we also want to, of course, take quotients by group actions. So let's say M is a complex manifold and G is a group. Which acts on M holomorphically. So this is an action such that. So, well, of course, we can always take a quotient, and this will be some topological space, but in order to make sure that the quotient is a complex manifold, we need some non-trivial conditions. Well, of course, first of all, I said that the action should be holomorphic. Well, this means that for any element of this group, the corresponding map, so gamma acts on M, so this gamma as a map from M to to itself is a morphism from M to M, or just a holomorphic map, right? So, and then we need more actually. So if we have such an action, then the quotient will not always be a complex manifold. So an example of a good action when we can take quotients is given by the following two conditions. So the action should be free, first of all. So the action is free. Well, everybody knows what free means, right? And the action is totally discontinuous. So what does this mean?
Each point has a neighborhood that is disjoint from all its images and is a group action.
Yeah, right. So that's a condition I would have in mind, but I would guess that this might be not enough also. So what I would mean here is that any compact set, so okay, so let me write it down. So this would mean that for any compact set in M, the collection of, well, the set of elements of this group G such that K intersects its image under gamma. And so I want this set to be finite. I think this is stronger actually than what you've said. So what you've said follows from this, but this is stronger, and this in particular is needed to make sure that the quotient is Hausdorff actually. Okay, so, well, let me write it as an exercise. Well, I will first of all, so I will call the quotient n. So n is M mod G with the quotient topology, and the map from M to n is called pi. So, exercise. Well, first check that for any x in M, the orbit is a discrete subset of M. Then, well, you can also deduce this property that was mentioned, so that every point in M has an open neighborhood such that U is disjoint from all of its images, so namely that this intersection is not empty if and only if gamma is the identity element. And well, then you can also deduce that n is Hausdorff. Okay, so then in particular from this second part it follows that every point in M, so if I take such U as in 2, so take U as in this second part, and then it follows that the image of U in N is homeomorphic, somehow that pi is a homeomorphism from U to its image. And then we cover N by such images or such subsets, and then we get in such a way an atlas on N, so that this U may be taken small enough so that it would lie in some coordinate chart on M, and then we cover N with the images of such subsets, and we get a cover of N, and then we get a structure of a complex manifold. On N. Okay. So what are the examples? So I want to give two very basic examples where this construction can be used. So let's call this for A. Example for A, I'll take just the lattice Z2M, and my manifold M will be Cm. So of course this Z2M, it acts by translations. So Z2M is embedded into Cm, well, as a lattice, for example, like this. So this is a subset in Cm, and it acts by translations. So the action is by translations. So the quotient is a compact complex torus. So M mod G is a compact complex torus. So that's another important example of a Keller manifold. And another example is, so let's take G equal to Z. And for M, let's take, let's say Cm minus 0. So then let's define the action of this Z on M. For this, let's fix some real number. For example, greater than 1. And then the action is by dilations. So I take some element from Z, so K, for example. So K dot X will be lambda to the power K times X, right? So the action is like this. Well, so what is the quotient?
S1 times S2M minus 1.
Yeah, right. So the quotient, so this is called a Hopf manifold. S2M minus 1 times S1. So for M equal to 1, we just get an elliptic curve, actually. S1 times S1. And for M equal to 2, we get a Hopf surface. And the Hopf surface is a basic example of a manifold which is not Keller, actually. So we will not say too much about these Hopf manifolds. Well, actually, the higher dimensional Hopf manifolds are also non-Keller. But it's nice to know an example. So this is always a complex manifold, right? Well, finally, well, then one just last construction, which is also always used, is the blow-up. Let's recall how to construct the blow-up of C2, for example, in a point. So this will be 5. Blow-up of C2 in a point. So I take C2 and well, let me take the product of C2 and CP1. And let's consider M, a closed subset here, which is given by the following condition. So I take points x, y in C2 and a point in CP1 with coordinates z0, z1, and I want them to satisfy the following condition, z0y minus z1 x equals 0, right? So then this is actually a complex submanifold in M, as you can easily check by example, whatever it was, 2, I guess, by example 2, N is a complex submanifold. Of M. Well, so why is it called a blow-up? I'll just recall. So if we look at the projection now, at the projection to C2, well, let's restrict this projection to M. Then the fibers of this projection look like this. So what are the fibers? If I take some point xy, then if xy is not the origin in C2, then actually this point z0, z1 is uniquely determined from this equation, right? So then it will be just x, y, and the point in CP1 with homogeneous coordinates xy if this is not 0. And otherwise you'll get the whole CP1, right? So if xy is the origin, then here I get 0 for any z0, z1. And so the pre-image will be this whole thing. So actually what I do here is that I throw away the origin and I glue in the set of lines through the origin, right? So that's the blow-up. So if xy is 0 here. So if you have never seen this, well, it's useful to, well, to do the exercise and construct the blow-up of a manifold along arbitrary smooth submanifold. It's done exactly the same way. So exercise. Construct the blow-up of M in N for any complex submanifold N inside M. Okay, So now, so actually the next thing. So are there any questions, by the way, about this? All right. So then let's go on. And first thing I wanted to talk about actually, which is closer to the subject of Kähler manifolds, is the complex structure operator on a complex manifold. Okay. So if we have our manifold M, then it is in particular, so this M is a complex manifold. So then it is in particular a real manifold of dimension twice the complex dimension of M, and we have the real tangent bundle of M, which I will denote like this. So this is the tangent bundle of M as a real manifold, real or differentiable manifold. Well, I wanted just to recall some things about vector bundles and about how to construct them. I recall that if M is a differentiable manifold, then a vector bundle E over M is a differentiable manifold, a differentiable manifold E together with a projection from E to M such that there exists a cover, open cover of M, and local trivializations of E over the elements of this cover, so and diffeomorphisms let's say eta alpha from the pre-image of U alpha to Rk times U alpha that satisfy some conditions. Such that well, first they commute with the projection to the base. So we can write it like this: the projection to U alpha composed with eta alpha is equal to pi restricted to the preimage of U alpha, right? So I just take this eta and then I compose here with the projection to the second factor. And the second condition is that, okay, so in particular, the fibers of this map pi are all isomorphic to the vector space Rk, And then the second condition is that if we go from one such local trivialization to the other, then the transition functions are linear along the fibers. So for any pair of elements of this open cover, if I consider the following composition, so eta alpha beta, which will be eta alpha composed with eta beta inverse. So this goes from Rk times the intersection to itself. So we know that this map will preserve the fibers of the projection to U alpha beta, but we ask more, so we want that there exists some continuous or differentiable map. So for example, mu alpha beta from the intersection into GLK, right? Such that well, this map eta alpha beta of the point V comma x is equal to, well, so I take the map mu alpha beta, so I get an element, a matrix, k by k matrix, and then I apply it to this vector V. So this will be mu alpha beta of x applied to V and comma x. So like this. So these transition functions are just linear along the fibers, right? So then these maps mu alpha beta, they form a co-cycle. And to define a vector bundle, we just need to give ourselves such a co-cycle. So a remark here is that so mu alpha beta satisfies, or so the collection of such functions. So all these functions satisfy the co-cycle condition. Well, so this just means that if we take the product mu alpha beta, mu beta gamma, mu gamma alpha for any point, this will be the identity matrix, and this is for any point x in the triple intersection, like this. Right, and also, well, you can write also some other conditions that should be satisfied, is that this thing is just the identity also for any alpha. Okay. And if we have such a co-cycle, then we construct a vector bundle. So what are the operations on vector bundles that we can apply? So let's say we have E1, E2, two vector bundles with co-cycles mu alpha beta, and well, and let's say nu alpha beta. So if we have two vector bundles, we can always take a refinement of this open cover so that both co-cycles would be defined on the same cover. So then what can we do? So we can do all the operations that we can usually do with vector spaces. So for example, we can take the dual of E. So So this is the dual. So the co-cycle here. So how to define the co-cycle for the dual?
Inverse of transpose?
Yeah, right. So this will be mu alpha beta inverse of transpose. So then the direct sum. For the direct sum, we take these two co-cycles. So at every point in U alpha beta, we have two matrices. And then we form a diagonal matrix with this mu and nu on the diagonal. So we have here the co-cycle of the following form: mu alpha beta 0, 0, and mu alpha beta. Okay, so we can form tensor product. So here the co-cycle will be given by the tensor product of two matrices, which basically means, so how to write this? So if I have two matrices, A in GL KR and B in GL LR, then the tensor product acts on some decomposable vector in the tensor product of these two vector spaces of dimension k and l, just in the obvious way, like this. Right, so then by using this operation we can form the co-cycle, which is the tensor product of two co-cycles. All the conditions will be satisfied, so this gives us a well-defined vector bundle. And well, so on. So there are many other things you can construct. For example, you can construct the bundle of homomorphisms from E1 to E2. This is just E1 dual tensor E2. You can also form exterior powers, symmetric powers of your vector bundles, because, well, if a matrix operates on some vector space on the dimension k, for example, then you can somehow this induces an action on the exterior powers and symmetric powers of this vector space. So all these natural constructions can be applied to vector bundles as well, and so on. So is everybody familiar with this actually? All right. Okay. So then let's just, well, one small remark here is also that we will always also identify vector bundles with the sheaves of sections. I will be a bit sloppy here, but I hope this will not cause any confusion. So of course we can consider sections of vector bundles, and those sections, they form sheaves. So sections of a vector bundle of a subset U, or we can also denote it as before, just E of U like this. So this is the set of maps from U to E such that pi composed with S is the identity. And so this, well, of course, S should also satisfy some natural conditions. For example, if E is a differentiable bundle, then this S should be also a differentiable map. Differentiable or probably holomorphic, real, analytic, and so on. So whatever type of a vector bundle we have, we will have the corresponding sheaf of sections, and I will just write somehow. So E will be also somehow I'll write E for this sheaf as well, not only for the somehow for the topological space, but also for the sheaf of sections. E also will also denote the sheaf of sections of E. So now if we go back to this tangent bundle, so we have our transition maps for a manifold M. So they were defined like this. Right, so these are maps from some open subset, from open subsets in Cm to some other open subsets in Cm, and they were holomorphic. Well, let's denote the components as before. So this phi alpha beta is given by the holomorphic functions f1, fm. But we may also view them as maps of from R to M to R to M. So we will denote the real and imaginary parts like this. So let's write that I equals xi plus imaginary unit yi, and then this fj of z1 and so on zm equals uj of x1, y1 and so on xm, ym plus imaginary unit times vj x1, y1 and so on xm, ym. Well, then let me recall that these functions uj and vj, they satisfy Cauchy-Riemann equations, right? So if I look at the following matrix, so let me denote it by jij. So the partial derivative of uj over x, I want to take ui over xj, then dui over dyj, and then dvi over dxj and dvi over dyj. So these partial derivatives, they satisfy Cauchy-Riemann equation because the functions are holomorphic. And those equations look like this. So dui over dxj equals dvi over dyj, and du over dyj is minus dvi over dxj. Or this is equivalent, so this is if and only if this matrix commutes with the following matrix, with the matrix of the following form. Okay. And then the Jacobian matrix of this map phi alpha beta, so the Jacobian in the sense of somehow of the real, somehow as the Jacobian of this map as a real map from R to M to R to M, it will be a block matrix consisting of such blocks, and so they will all be somehow complex linear, so that they will commute with the complex structure operator. So let's call this Jacobian matrix. So this will be J alpha beta, and I put R here so to emphasize that this is somehow the Jacobian of this mapping as a map from R to M to R to M. So Jacobi matrix of phi alpha beta is a map from R to M into itself. So this is a block matrix consisting of blocks Jij. So this, and also so this is exactly the somehow this J alpha beta, it gives a cocycle. So this is a cocycle for Tm. So since it commutes, it consists of those blocks that commute with that matrix 0, minus 1, 1, 0. So then this J alpha beta commutes with the matrix I, which has such blocks along the diagonal. Right? So then if you think about what it means in terms of vector bundles, this means that this I actually defines a section. So I defines a section of the bundle of endomorphisms of Tm. Right? Well, if you are not sure, then you should think about it. So as an exercise, check this. So if you just think about how you define this bundle of endomorphisms in terms of cocycle and what it means to have a section of this bundle, then this condition is exactly that you have a section, right? So that this matrix commutes with I. All right, so this I is called the complex structure operator of a complex manifold. Well, it acts on the vector fields in the usual way. So if we, so if we consider the coordinate vector fields, then the action is given like this. So I times d over dxi equals d over dyi, and here it is a minus d over dxi. Right, so we can consider the eigenspaces of this operator in the complexified tangent bundle. So these are the usual holomorphic and anti-holomorphic vector fields. Well, they are eigen vectors for this operator I. And so if we consider the subbundles spanned by these vector fields, we will denote them by T10 and T01. Okay, so then the complexified tangent bundle will be the direct sum of T10 M and T01 M. So this subbundle is, so this is locally spanned by d over dzi, and this one by d over dzi bar. And the point is that, so last thing I wanted to say today is that we can actually do the converse. So we can start from some real manifold and consider an operator I like this. So, and then if this operator satisfies one additional natural condition, then we can conclude that this real manifold carries a complex structure. So the structure of a complex manifold, I mean in the sense defined today, such that I will be the complex structure operator. So the condition that we should check actually when we consider such operators I is that the sections of, or local sections of the subbundles, they are closed under Lie bracket. So we can note easily that in our case, so when we started from the complex manifold, then obviously, so these vector fields, these holomorphic vector fields commute with each other. And this implies that the subbundle T01, T10, T01 also, so T10 is closed under Lie bracket. And well, that's the condition of integrability for the complex structure. So let's give a definition today, and then I'll go on next time. So the definition is like this. If we have some, so let M be a real manifold of dimension 2m, of real dimension 2m, then I, which is an endomorphism of the tangent bundle, is called an almost complex structure if I squared is equal to minus the identity. So in this case, so if I is an almost complex structure, we have a decomposition as before. So the complexified tangent bundle decomposes into the direct sum of two eigen subbundles, T10 and T01. So T10M is eigenbundle for I with eigenvalue square root of -1, and the other one is the complex conjugate. Well, and then I, an almost complex structure. Is called integrable if well, the subbundle T10, for example, is closed under Lie bracket. And then the theorem of Newlander-Nirenberg tells us the following, that if we have a real manifold M with an integrable almost complex structure, well, let's write this real manifold M with an integrable almost complex structure admits a structure of a complex manifold. So the almost complex structure is called I here. So then M admits a structure of a complex manifold such that this I is the complex structure operator. So if we have this I, this operator I with this condition, then we can always find the collection of holomorphic charts as in the sense discussed in the beginning of today. So I thought that I would not like to give the proof of this theorem. Actually, it's quite difficult to prove it. So has anybody studied the proof? So I'll have a look by next time. So perhaps, so it's relatively easy to explain the proof in the case when M is a real analytic manifold. So this can be done more or less easily, and I'll probably try to do it next time quickly, and then we will go on and discuss possibly something related to the Hermitian bundles and Chern connections. So do you have any questions? Okay, so I think there is no one in Zoom, although people have asked me to give them links, but no one joined actually.
Maybe they will got the videos, right?
Yeah, perhaps. But they don't need the link to the Zoom meeting if they don't want to come actually. So I don't know. All right, then that's all for today, and then see you next week, I hope.